useful property of signals related to the symmetry and the time reversal. So you can check for the evenness and oddness of the signals in terms of reflecting or in terms of the symmetry or reflecting the signals around the vertical axis. So this property is related to the symmetry under the time reversal operation. So either you can have an even signal. Okay, for an even signal, if you, for example, apply the transformation of time reversal, you record back the original signal back. Okay, so for example, if you have a signal like this, any arbitrary signal, okay, which is time limited, let's say from minus t naught to plus t naught. Now, if you're going to, and this signal is xt, right? So if you're going to flip this signal around the vertical axis, this is the vertical axis. Okay, if you're going to flip the signal around the vertical axis, under this transformation, the signal remains unchanged. Okay, so you see, if I'm going to flip this, it's still the same. This is x minus t with the same time bounds on either sides of the time axis. So this is again minus t naught plus t naught. Okay, so the signal, we say the signal is even signal. Okay, so signal xt or xn is referred to as an even signal if it is identical to its time reversed counterpart. It means with its reflection about the origin, there's no change in the signal, so that's an even signal. So in continuous time, signal is even if this relationship holds. And if it is discrete, the same analogy holds in the discrete time domain. If you're going to flip the sequence around n equal to 0 axis, there's no change. If you're going to apply the time reversal, discrete time reversal, there's no change in the original signal or the original discrete time signal samples, right? So again, a signal could be odd if you apply the time reversal, then the signal is itself, but it comes with a negative sign. For example, consider the signal like this. Okay, you have a let's say a continuous time signal like this. That's it. It's not a sinusoid, but this is the time limit from minus t naught to plus t naught. It exists between these two time limits. It's a time limiter signal. Okay, this is your xt. So you can see this is not an even signal, right? This signal is not an even signal. Why? Because if you're going to apply the time reversal, it's going to look like this. If you're going to flip this, it's going to be something like this, right? So this is minus t naught, and this is plus t naught. Okay, this is your x of minus t, and how you obtain the time reversed version of the original signal, you just flip this into considering the vertical axis as a mirror. Okay, so the vertical axis is the mirror, and you just flip this around. So this is of course not equal to xt. This is not the case, but you can make this equality work if you put a negative sign with xt. Okay, why? Because if you multiply this with negative sign, then this the negative time axis, amplitudes, they come up like this, and on the positive time axis, the amplitudes, they come down like this, and this is exactly what is happening over here. So you see, this negative sign has to be incorporated for this case for the equality to hold. So for odd signals, the flip versions, they're going to be the same as the original signal, except that the original signal has to be multiplied by negative sign. Okay, and the same analogy holds for the discrete time sequences. So, but this an important constraint that comes with this with the odd signals is that an odd signal must necessarily be 0 at t equal to 0 or n equal to 0. For example, consider a signal like this, which is an odd signal. Okay, so I'm going to cook up an odd signal like this. This sample has to be 0. You see, this could be 1, this could be minus 1. Okay, and this sample is at 0, this is at 1, and this is minus 1. And you can see this is not an even signal. Okay, if you're going to flip it, this is x of n. If you're going to flip it around n equal to 0, under this time reversal, what's going to happen is 1 is going to come over here, and then at so this is minus 1, amplitude becomes 1, and then at 1, at amplitude minus 1. So this is your minus n. Okay, and if you recall, the sample at n equal to 0 is 0, right? So this is the situation if you reverse it. But if you multiply the original signal with minus, then this would correspond to x minus n, right? If it is multiplied with minus 1, then this sample is going to reverse its sign, this is going to reverse its sign, and then you have the same thing. Okay, so this is an OR signal. Fine. But the constraint that I'm trying to emphasize over here is there is no way you can have any arbitrary sample. You cannot have, for example, 2 over here, a sample that takes the amplitude of 2 or 3 or minus 1, whatever. Okay, it has to be 0. Why? Because you see x of 0, if at n equal to 0, x of 0 is what? It's minus x of 0. Okay, so it cannot be 2 equal to minus 2 or 1 equal to minus 1 or 10 equal to minus 10. Okay, this only implies that x of 0 should be identically equal to 0. That's it, no other way. So therefore this enforces the sample at n equal to 0 or at t equal to 0 to be 0. For odd signals and odd sequences, it's important that at 0, at n equal to 0 or at t equal to 0 or at n equal to 0, the above equation holds for odd signals. It requires that x0 equal to minus x0 and x0 is minus x0. Therefore, the sample should be necessarily 0. Okay, it cannot be 2. It cannot be minus 3. So this is not the case, right? You cannot have it minus 2, right? So for odd signals, it's important that 0 should be plus minus 0 is the same thing. That's the philosophy. Okay, so this is a further example of even and odd. You can see this signal. If I flip this around the vertical axis, the flipped version will be the same as x of t. So this is an even signal. So the first signal is an even signal. In part B, x, if I'm going to again flip this vertically around the vertical axis at t equal to 0, then this is going to come with a negative sign. Okay, I have to multiply the flipped version with minus so that I can get back x of t, right? I mean, you can visually look at what's going to happen. If I'm going to flip this over, it will be something like this first, okay, and then over here, this is my flipping. This is I flipped it, but if I multiply this negative, then this is what I reconstruct, what I construct. Okay, so for an odd signal, xt is minus x of minus t, right? Okay, now this is how you define an even signal and odd signal. But arbitrary signals are out there which are neither even and odd. An example is like this. This signal is neither even, neither it is odd. You can see that if I'm going to flip this around n equal to 0, it doesn't correspond to x of n, right? It's neither even, it's neither odd. But an arbitrary sequence or a signal can be decomposed into its even and odd components. For example, consider this signal. Well, this signal is precisely equal to half x of n plus x of minus n. Now this becomes the even part of the signal of the sequence x of n. You see why? It's very easy, because x minus n is it's simple to see. X minus n is still equal to x of n, right? if it is even, if you're saying this is an even part, then x minus n, philosophically x minus n should be equal to x of n, which means that this should be the same, right? So this signal is the even signal. So for example, if I'm going to we have decomposed, we have just extracted the even part of the signal, and this sequence is an even sequence. Now you see, if I'm going to flip this around on the vertical axis, I don't care what the sample at n equal to 0 is, because it's an even signal. It can be any sample. You still get back your even part intact. Okay, so time reversing this sequence around n equal to 0 is going to return you back your original sequence. So it is still an even signal. Okay. You see, what happened over here is that analytically, if you add x of n, all the samples are 1 for n greater than or equal to 0, right? And if you look at this expression, xn plus x minus n corresponds to the samples like this. Okay, so at n equal to 0, we're going to have 2, right? And then for n equal to 1 plus minus 1 on either sides, there will be 1. but not exactly 1, then they will become half, right? So because we have a half over here, so this is going to be 1. Okay, this is going to be 1 by 2, and this and this samples continue on either side of the n-axis, right? These all samples are of the amplitude 1/2. So this is an even signal. If you want to call this signal as E of n, this is indeed an even signal. You can see that E of n is E of minus n, and we call this E of n as an even decomposition or an even constitution of the signal x of n, which is neither even nor odd. So you're just extracting the even part of the signal by considering half x of n plus x minus n. Okay. Similarly, you can extract the odd part from x of n. The philosophy is the same. So what you can do is, since you're extracting the odd part, so you can have this as x of n minus x minus n, because odd signal x minus n is equal to minus x of n. So these two quantities are equal, and then this becomes twice x of n, and this 2 cancels over here half by half. So again, you see, if you do this manipulation on this x of n, it enforces 0 at the origin. So in which axis, if you're going to flip the sequence, you're going to produce the same sequence if you're going to multiply this with the negative sign. Okay, so this is indeed an odd signal. Okay, I mean, the manipulation is very easy. You just have to add up xn and x minus n. You just have to subtract that, because x minus n is going to be coming on the other side, and then with the negative sign, the sample becomes with minus 1 by 2, just like over here we had 1 by 2, so these will be minus 1 over 2 because there is a negative sign over here. For positive indices, this will be plus 1 by 2. For negative n indices, it will be minus 1 over 2. But at n equal to 0, what's going to happen is 1/2. This will be x0 minus x0. Okay, minus x0. So the two samples are the same. So you see, the odd decomposition must enforce a 0 at n equal to 0. This 0 is occurring at n equal to 0, right? This is important over here. This is an odd decomposition of the signal. So you see, and any arbitrary signal can be decomposed into its even part or its odd part, and in general this is true. So an important fact is that any arbitrary signal can be broken into a sum of two signals, one which is even and the other which is odd. So to see this, if we consider a general signal which is continuous time, the same analogy holds for the continuous time as we've seen for the discrete time. But the even part of any arbitrary signal xt is, the even part is half xt plus x minus t. And if you are going to, you see, since if you're going to replace t by minus t, nothing is going to change. Okay, so if you change this to minus t over here, and you bring minus t, then this becomes plus. This expression remains the same, and this expression should be the same. So that means the signal, the even part of the signal xt is indeed even. So this is referred to the even part of the signal. Similarly, you can work out the odd part, just like we did for the discrete time case. Similarly, again, if you are going to replace this with minus sign over here, you replace you're reversing the time reversal. You're applying the time reversal to an odd part of the signal. So this is minus, this becomes plus. Then this has to be replaced with minus as well. Okay, this has to be minus, and then this is plus. Or you keep it as it is. The right hand side, on the left hand side you multiply with minus. The effect is the same. So again, and this is in fact the odd signal. Okay, so this is exactly analogous definitions, and the exact analogy also holds in the discrete time case as well.